Saxon Advanced Mathematics, Lesson 70. We're going to talk about statistics a little bit more, ladies. We're going to go back to the standard deviation conversation that we were having, and we're going to look at those normal curves that we talked about. And remember that last time we talked about that if you gather enough scores, a set of data, it will create this approximate curve, which we call a normal curve, and we can find the standard deviation, which is the measure in which 68% of the data falls. And if we measure two standard deviations, we'll get 98% of the, no, 95, sorry, 95, and then this is 99% is three standard deviations. We mark the mean right in the middle, and then we measure one standard deviation, 2, and 3, and it gives us lots of interesting information. Now, the thing is that sometimes we don't want to have these raw scores. That's what we call those on here. We don't want to have this kind of random stuff. What we want to do is put the mean in the middle and set that at 0. Then what we can do is we can calculate the standard deviation and measure, this is, what we do is we take the actual score, subtract it from the mean, right? So 140 minus 150, that would be minus 10. So that's why we have a minus 10 here. 160 minus 150 would be positive 10. And then if we divide those out one more time, we see that we've set this up so that we have a 0 at the mean, and then we've got it measured. I think Grace is chewing a bone, and she's going so crazy that she's knocking all of my papers sideways and crookedy because my math books are on the couch. All right, so what this does it allows us to make different normal curves and then compare them more readily, okay? Now, what we also are interested in doing is finding where somebody stands in percentile. So let's say that these are all the grades in a class, and your grade is out here at 2.14. What we want to do is be able to calculate what percentile does that put you in. That would probably mean that about 99% of the scores were behind you, but we want to be able to measure that accurately. So what we do is we calculate something called a z-score. This will make a lot more sense when we do the examples, you guys, by the way. We'll do something called a z-score. I'll write this down in just a minute. We calculate a person's z-score, or where that piece of data is, and then we use this table, called a standard normal table, to turn their z-score into a percentile. Let me show you the way that works, because that just sounds really, really weird right now, right? So, to calculate a z-score, Grace is burying her rawhide bone, by hiding it under the table that I'm working on. We use this formula. Where x equals the individual score, this letter is the mean, and this, as we already know, is the standard deviation. Okay, so this z-score is the middle step. Then, to find the percentile, which is what we're really after, we look up the z-score in the table. And I'll show you how to do all this, okay? Like I said, this makes a lot more sense when you have a problem. So hold on to all of this and let's figure this out. The mean weight of the babies born in a metropolitan hospital for 7 years was 6.8 pounds. Okay, so the mean score equals 6.8 pounds with a standard deviation of 0.8 pounds. If the distribution of weights were approximately normal, which means all of this is going to work, what percent of babies weighed less than 6.4 pounds? So we want the percent of babies weighing less than, what did I say? 6.4 pounds. Okay. So the first thing we do is we calculate the z-score of 6.4 pounds. So we take the number that we're interested in, 6.4, the individual score. We subtract the mean, which is 6.8, and then we divide that by the standard deviation. This is the formula I'm using, which is 0.8. So in this one, it would be what? 0.4 negative over 0.8. Make sense? And that simplifies to negative 1/2 or 0.5. I'm trying to squish that in. So now we know this is our z-score, minus 0.5. So now we go to our table here. And it was minus 0.5. So what we need to do is we need to find the z, so the first digit of the z-score here. It is 0, but it's a minus 0 value. So we know that it's going to be this one, not the positive 0. That would be if it was positive 0.5, for example. But we want negative 0.5. So there's our 0, and then we scoot down here to 0.5. So that number is 0.3085. Okay, so our z-score we calculated is negative 0.5. The percentile on the table for a z-score of minus 0.5 is equal to this. So that means 30.85 of the babies weighed less than 6.4 ounces. That's our answer. Okay? So it's cool because John gives us some information, and then we're able to use a few simple formulas and a table to find out some really interesting information. Let's do another one. For the example in 70.1, this is now example 70.2. What percentage of the babies weighed between 6 pounds and 7 pounds? Okay, so we're going to calculate 2 percentiles. We want to know about 6.0 pounds, and we want to know about 7.0 pounds. 7.0, not O. That's bad. Okay, our mean was 6.8, and our standard deviation was 0.8. I'm copying that from the other problem. All right, so at 6 pounds, we need to calculate our z-score. That would be 6.0 minus 6.8 divided by 0.8. Okay, that is 0.8 negative over 0.8. So that means it's negative 1.0. Make sense? Now, we'll do the same thing for our 7-pounders. 7.0 minus 6.8, right? Because it's actual. The formula is that's our z-score. The actual data minus the mean divided by the standard deviation. Our mean is 6.8. Our standard deviation is 0.8. So there's the setup. That's this calculation for our 7-pound babies. And this becomes 0.2 over 0.8, right? I just subtract. And that's the same as 1/4, so that's 0.25, whoops, 0.25 positive. So now we go to our table, and we're going to find the percentile for the 6-pounders and the percentile of the 7-pounders. Here's our chart. Our first number is minus 1.0. Minus 1.0, so that's 0.1587. That's our percentile. Our 7-pound babies have a z-score of 0.25. So it would be 0.25. So there's the 0 and there's the 2. But where do we get 0.25? Well, we don't have that option. So what we're going to do is we're going to average those two scores, the 0.2 and the 0.3, and figure that 0.25 would be halfway in between. So we take those two scores, which are 0.5793 and 0.6179. And we're going to add them and divide by 2. And I'm going to let John do the heavy lifting on that. That will be 0.5986. So what that means, let me just draw you a chart. I didn't do that for the other one. Okay, there's our mean. Our mean, pretend it's perfect. Our mean is 6.8, right? And so what that means is that our babies who are at 6 pounds are fairly down here. They're like at the 15th percentile, 15.87, right? This would be 50% because it's the mean, so it's halfway. And then our 7-pound babies are up here at 59.86%, right? Those are our two calculations. And so the question is, how many babies, what percentage of babies weigh between these two? Okay, well, we'll take the 70-pounders represent 59.86, and then it stops here, right? This is 7 pounds. This is 6 pounds. So what we can logic out is that we need to subtract 59 minus 15.87, and that will tell us how many fall in here. That's the logic. This 59% represents everything. 15% represents those. So if we want the gap in between them, we subtract. And the number that we get is 43.99% of the babies fall into this category, between 6 and 7 pounds. That's kind of fun, I think, to know that we can manage the data in such a way that we can get answers like that. And we just have one more problem in the same hospital. So in other words, the mean and the standard deviation are the same. What percentage of babies weighed more than 7.2? So we want percent of the babies weighing greater than 7.2. Okay, so we use our same information. X minus mu divided, I think that's pronounced mu, equals that. That's the z-score, right? Where X is the individual, mu is the mean, and omega is the standard deviation. Okay, and in our hospital, the mean was 6.8 and the standard deviation was 0.8. We never figured this out. That was given to us all the way through. Okay, so for 7.2 babies, We subtract 6.8, the mean. We're going to divide that by 0.8. This will be 0.4, right? 0.4 over 0.8. And that simplifies to 1/2, which we'll write as a decimal. So that's our z-score. So we take that to our table. Now it's positive 0.5. So this time we'll want to use the positive 0. And we'll run down to the 0.5, 69.15. It's okay to convert this immediately to a percent rather than writing it as 0.6915. You can leave it in this form, or you can convert it to the percentage form just by moving the decimal place twice. You can work with the number in either form. It doesn't matter. The answer wants it in this form. And to me, I like to change it right away because that makes it more of a number I can wrap my head around. What this tells us is that with these babies, there's the mean. This was 6.8, so this represents 50%, right? And then we have, I'm going to try and draw it a little more carefully. Oh my gosh, I'm so sorry. We're trying to find out how many babies weigh more than 7.2. So let's just put them right there. I'm not measuring out the standard deviations carefully. That's not important to this problem. What is important is that what we want to know is the number of babies here that are greater than 7.2. But this percentage tells us this percent. It tells us how many babies are here. But we want to know how many are over 7.2. So what we have to do is we have to take 100%, all the babies, and subtract 69.15. And that will give us 5803. So that means that 30.85% of the babies are in this group, right? Because the percentile measures everything behind the line, if you want to think of it that way. Everything to the left, and then to the right is what is the babies that are higher. So in order to get this area that we're interested in, we have to subtract that because 100 is out here, right? And we figured out that this is roughly 69%. Okay, so we weren't interested in this number, which is what the 69 represents. We're interested in everything above there. Okay, so these are fun because the calculation is easy, but it's fun to kind of play around with these scenarios and try to figure out what exactly John is asking you to do. There is variation. The common multiple in all of these problems is the data here. Calculating the z-score, looking up and finding the percentile in the table. This is the information we need to calculate the z-score. And you know, people might ask, why? How did these z-scores work? Well, these tables were developed. And the z-score is what allows us to dip into the tables and read them accurately. When I was coming up in algebra, this is how we did all of our logs, and this is how we did all of our trig, was in tables like this. So maybe someday this will all be programmed into your calculator, and you'll just enter, you know, you might just enter these 3 pieces of information and go directly to the percentage. But for now, we get to use the table, and it's kind of fun. All right. Hopefully this makes sense to you. It feels a little wobbly because we're not used to talking about these things, but the calculations are straightforward, and I hope they feel reasonably simple. That is lesson 70. Thank you. Goodbye.